Okay, so I think the big thing here is, can we practice writing exponential functions, and then can we practice using exponents? Okay, so I think the first thing is, reminding yourself, 8 to the 0 is 1, 10 to the third is a 1 with 3 zeros, 2 to the negative third is 1 over 8, because you cube it and you do the reciprocal. This one you cube it and you do the reciprocal, so it'd be 512, and this would be 1 over 10 to the third, or 1 over 1,000th, which is 0.001. Okay, if you divide those, you would read them or put them the same way. So both of these are true. Normally we work with fractions, but it is true as well. And then remember, if you do 0.3 to the third power, you could do 0.3 times 0.3, which is 0.09. Okay, that you get the same answer if you go 3/10, which is 0.3 as well. 3/10 times 3/10, which is going to be 9/100. Okay, and then you're going to times it by 3/10 again, which will be 27 over 1,000. Okay, if you multiply this by 0.3 again, you get 27 with 3 zeros, so it'd be 0.027. So these are both the same answer, but I want you to know how to kind of think through, what are we doing? Okay, the introduction for today, and normally for the whole unit, is, if you have a single sheet of paper and it is 0.0038 inches tall, if you double that by, either folding it in half or just getting 2 sheets of paper, it'd be twice as tall. So it'd be 0.0076 inches tall. Okay, that would be one doubling. If you double it again, there'd be 4 sheets of paper. So you double that height and you get 0.0152 inches tall. Okay, so let's think about, the more times you double, you get twice as many pieces of paper tall, and you double the height of your stack. So 0.0304. And then 16 sheets of paper, so that'd be 2 doublings, 3 doublings, 4 doublings, etc., is going to be 0.0608. What if you double the original piece of paper 25 times? How tall would your stack be? And if you think about it, we want to times this sheet of paper by 2 25 times. So 0.0038 times 2 to the 25th would be our answer when we multiply that out. And that'd be just over 2 miles tall, which is kind of crazy, okay? And so doubling something really does make it grow substantially, okay? And let's think about, we've talked about over the last couple of days, graphing exponential functions where there's a variable in the exponent. And if you made a table, you would say, okay, if I plug in 0 and 1 and 2 and -1, you would get these values here. Okay, and so we've talked about, it's doubling each time. Well, if we're comparing this to the function y is equal to 0.0038 times 2 to the x, notice they're both the same parent function, but the one that we just did with the paper is going to be a vertical compression by a factor of 0.0038. So it's very much shorter and smaller than what the other function would be. It would still get very large, at some point after doubling, because doubling does change it quite a bit. However, I want you to think it is a vertical compression. Okay, and so here's talking about those parent functions. If you have a graph, if you have the same base value of the b, then they will be parent-child. Adding or subtracting to the x is going to be left and right movement, vertical compression or stretches in front of the function, and k will raise or lower your asymptote. Okay, so again, if the b value is greater than 1, it will be growing. If it is between 0 and 1, it will be falling. And so I want you guys to be able to do this kind of graphing without a calculator. Okay, and I think the big way to do it is to say, what is the parent function? How does this compare to the parent function, and can I graph it? So the parent function of this first graph would be f of x equals 1/2 to the x. Okay, and so that's an x there. Okay. It looks like a star or something weird. And the 8 does a vertical stretch. And so it doesn't move left or right. So you can begin with 0 and pick a couple points on each side to be able to make the shape. Okay, and so it will be falling because the factor is going to be decay. So you do 8 times 1/2 to the 0. Do a half to the 0 is 1 times 8 is 8. 1/2 to the first is 8, is a half times 8 is going to be 4. And this would be 2. And then remember, -1 right here flips over the fraction. And so you get 2 for your fraction here, and then times by 8, this would be 16. So you can very quickly get a graph, okay, that falls if you just plug in some values and start with 0 and pick a couple points on each side of it. And you can say, hey, there's my graph, and that's what it'll look like. And so it will get close to the asymptote, which is the line y equals 0, without touching. Okay, the range is from 0 to infinity, not including 0. This next one has some transformations going on, and I want you guys to practice knowing, hey, this is going to be y equals 3 to the x, and the difference is a vertical stretch by 2. It's going to be right 1 and down 1. So the new asymptote is going to be down 1, and it's going to be right 1. What does that mean? Well, that means the center is not 0. The center is going to be at 1. So begin at 1. If it moves right 2, we'll start at 2 and then pick a couple points on each side. I don't care necessarily if you pick like 1 or 2 on each side, but it should work. So you probably are going to have to do 2 on one side and then 1 on the other side to get the shape, to get the trademark shape. But you can expedite your steps if you know it's moved right 1 and you start at 1 for the middle value. So pick a point to the right and pick a point to the left, and then see how many more points you need to graph to be able to get the trademark shape. And so we're going to do 2 times 3 to the 1 minus 1. So 1 minus 1 is 0. So 2 times 3 to the 0, which is going to be 2 times 1, and then subtract 1 is going to give us 1. And then, so 1 is 1. And then if you do 2, okay, 2 times 3 to the 2 minus 1 is 1. Okay, so 2 times 3 to the 1 is going to be 6 minus 1 is 5. So 2 is 5. If you do 0, 2 times 3 to the negative first, okay, so that'd be 2 times 1/3, okay, so that's be 2/3 and then minus 1. 2/3 minus 1 is negative 1/3. So if you do 2/3 minus 1 is negative 1/3, and you get right here. And so you can kind of start to see this is what your graph will look like. It's going toward the asymptote, which is going to be x equals -1 or y equals -1. And you could do the domain and range, etc., as appropriate. So I think the next thing would be, again, can you see that the +1 will raise it up 1? Can you make a table? Can you graph it? Can you see that's going to grow? Okay, and so yeah, you can make a table. Start with 0 because it doesn't move left to right, and that would be 2. You could plug in 1, that's 4. Plug in -1, that's 1/3 plus 1 is 1 1/3. So you can very easily get the graph of this to go cutely for you. Okay, the next one, it looks like it starts really high, and the y-intercept is quite large, okay? And so I think the big thing that you're going to do is that when you graph this, you're going to have to make sure you deal with the scale. But the basically, because it's not lifted up or down, the x-axis is still the asymptote here, okay? And if you made a table, of course you'd want to use a calc, but if you plug in 0, you're going to get 500. And if you count by hundreds, that's be 500 here. And if you plug in 1, you can say, okay, what is that going to be? But it's going to be up a skosh, okay, just a little bit. And so your graph is going to be climbing like this. And you can get specific values by plugging these into your calculator, okay? So practicing knowing what it looks like, what the transformations will be, what the parent function of each of these would be, and then talking about, can I do domain and range? Do I know where the asymptote would be? Okay, so let's move on to kind of the word problems. And I think the way that you do word problems most efficiently is to know that the coefficient in front of the growth factor is going to be the beginning value. And then the number that it holds up this is going to be the growth or decay factor. If it's bigger than 1, okay, this is going to be doubling every time you do the function. This will be tripling. This will be halving each time, okay? And so if that value, the growth or decay factor, is bigger than 1, it's going to be growing. If it's going to be between 0 and 1, it will be decreasing. So those are factors that will help us kind of see what is going on there. And so, we've talked about this before, is that, hey, this is growth by 30%. Why? Well, because 1 would be just staying the same, but 130%, if you put it into percent form, would be it's increasing above 100% by 30% each time. Okay, and this would be growth by 40%. This would be decaying by 20%, it's losing 20% each time. And this one is a trap. Okay. And so that's going to be exponential. Okay. And so I think in class, depending, on the year, sometimes I do more of your questions, but I think the big thing is, if you begin with something, the amount based on time is going to be 500, whatever you start with, and then you do 1.21 to the T. Okay, that's by growing by 21%. 500 decaying by 21%. Well, you do 100 minus 21, that's going to be 79%. Divided by 100, you get 0.79, and then that could be your function for that. So be careful as you write these. It should either be bigger or smaller than 100%, depending if it's growing or decaying. Okay. And so I think, as we're doing these, set them up with your beginning value. 1.043 would be this one to the T. 500, 100 minus 4.3 is going to be 95.7, so 0.957. That's a 7 to the T. So, and again, if I want you to write a function, write A of T. The amount of money you have based on time is equal to that. And so, I think depending what you're going to do, maybe you plug in T as 8. The next one asks you to say, what would you have after 8 years? And so you would go 500, and that's 6.25% to the 8th. Okay, that will give you how much money you're going to have. Okay, and how much money you would have would be $8,120.85. Well, pretend you're going to work backwards, okay? And we don't quite know how to solve this. We're like, okay, if I want to have $10,000, okay, if I want to end up with that, and I start with 500, how could I do that? And there are those who guessed and checked on their homework, but I think the big thing is maybe graph each side of the equation. Y is equal to this and y equals this, and graph and see where they cross. Well, be very careful when you're graphing these because y equals 10,000 is very high. You have to raise the y max to more than 10,000. This starts at 500 and grows up to 10,000. And so it starts with 5,000, so put a 5,000 there. Okay, but that will help it get there quicker. And so you do second calculate intersection. So don't increase the max very much. I mean, because it's not going to be more than like 50 years, but increase the y max to be up past 10,000 so that you can see if and when they cross. If you graph both of those, you will see 11.4 years. So by 12th year, you would have that. So graph both sides of the equation. So I think, at this point, we don't know how to use logarithms to help us solve this. So we're going to use our graphing calculator to help us to graph these functions. So it's losing 3%. So the amount you have is based on time. It starts with 15,500, and you're going to lose 3%. So it's 0.97 to the T. If they tell you the number of years and they ask you how much it's going to be, then great. When will it drop below 8,000? So look at 8,000, and you can graph each side of the equation. And if you see 8,000 and you start here and you see where will it cross, the answer to that function is going to be 21.7 years or by 22 years. Always give a decimal and then you can round it off as you need to, but give me the decimal so I know that you are doing a good job at that. So we will learn how to use a logarithms to help us solve this, but at the current time, set it up. Losing 15% is 0.85, okay? And then X goes here, or T, the amount of money based on time, or X, depending on what variable you want to use. When will it, if they say, oh, well, how much money will we have in 5 years? Put 5 as X and then find it. If it says, when will it fall below 100? You're going to graph Y equals 100. You're going to also graph the right side of the equation and going to see where they, if and where they cross. And it appears that it's going to be 14.17 years or by 15 years. Okay, the next one. What's the difference between this should have a parenthesis on it, and this right here? Okay, it appears that this is going to be decay, and this is going to be growth, each by 10%. Okay, keep trucking. I think, the other ones are pretty much the same thing. They're just practicing. This would be 1,000. Oops, I should get a pen. You would go the amount that it's worth based on time. It's going to be 1,000. If it depreciates, it's going to be going down in value. So 0.85 to the T. And they said put it as 4. So put this as a 4. Okay. And if you evaluate that, you're going to get $522.01. Okay. So there you go. This is going to be growing by this percent. So you're going to do 1.02 million started with and 1.195 to the 2020, and that would be in 14 years from that point in time. And you could evaluate and pay, okay, 12.35 billion. Okay, and so we could check and see, be like, hey, is that what we had in 2020? Next one starts with 10 bacteria and it doubles every hour. Well, that means you put a 2 here. It's not 1.02. What is evaluated after 15 hours? Okay, so this is our value, 10, 2 to the 15. And you would have 3,27680 bacteria. Okay, so the last thing that we're going to talk about is, sometimes they compound it annually and use that original function. Sometimes they're like, well, you know what? Let's pay out more frequently. Okay, which means if they pay out like monthly, say their annual rate is 3%, but they don't pay 3% just one time a year. They divvy up that payment in, maybe 12 payments or quarterly, 4 times payments per year. And the good news about that, or bad news, depending if they're paying you or you're paying them, is that you get interest on your interest, or they get interest on their interest. So if you start with $6,000, okay, and they're like, okay, our annual interest rate is 7%, but we're not going to pay it just, yearly, annually. They're going to pay it monthly. Okay, and so the way you figure this out is you do 1 plus, because again, it's bigger than 1, the rate in a decimal form, okay, decimal. Okay, so not percent, so 0.07, and they divide that up into how many payments per year, and it's the number of years per year, times per year that they pay you. They're divided up into 12 payments, and so they're not paying 7% every month, they're paying 7% divvied up into 12 payments. And then that means your exponent is going to be NT, the number of times they pay you every year for how many years that they're going to pay you out. So this is kind of a cute thing if you're getting interest on your money. And if you put that in your calculator, yes, use the fraction key, plug that in there, and your answer is going to be, I don't have the answer down. Okay. I'll have to try it. But if you did the quarterly, okay, it's going to be a little bit bigger. Okay. The more money you have, the bigger the percent they give you, the longer the years you put in there, it will make a bigger difference. If you don't have a ton of money, or it's not a big rate, or you don't leave it in a bunch of years, it'll be a matter of dollars. Okay. Or cents, or just not that big of a deal. But if it is a higher rate, then it could make a bigger difference. So if you take the 7% and they want to pay you quarterly, it means they divide it up into 4 payments. They don't pay you 7% 4 times a year, or just 1 time a year. They divide it into 4 payments. And then that means your exponent, the number of times they actually pay you, is 4 times a year for 10 years. And that will be, more than just yearly. Okay. If they did it yearly, it would be 6,000. Just annually, they call that. It would be 1.07 to the 10 years. So if you wanted to, you could figure out if it's just annually, they pay a lump sum, okay, or if they pay you monthly. And the good news about monthly, or bad news, depending if they're paying or you're paying them, is that you get interest on interest, and then quarterly would be in the middle between those values. So it's a good thing to kind of look at. All right, thank you. Have a good day.